So let us continue our discussion on module 1, and now we are going to discuss something which is very common in competitive examination. They usually ask a question based on this, and this is called as your critical thickness of insulation. All right, so in case of critical thickness of insulation, what exactly is happening? So let's say we have a wire and there is a certain radius to this wire. Let's call this as R1. And on this radius of wire, I provide, let's say, first layer of insulation. Or we can provide only one layer of insulation. It's just, let's call this as R2. All right. Now it has been noticed that whenever heat transfer is taking place and you want to reduce the heat transfer, so we can reduce the heat transfer with respect to insulation. There are situations when we need enhanced heat transfer, and there are situations when we need reduced heat transfer. Enhanced heat transfer are the situations where, like an IC engine cylinder, so there is a combustion going on and a large amount of heat is generated, and we want to keep the temperature of the cylinder to a optimum level, because if the temperature goes too high, then that particular uh, cylinder will start to function abnormally. Same thing goes with any computer uh, processor, or even a server, computer server also. If the temperature goes too high or runs too high without proper ventilation, without proper cooling, then the system starts to behave abnormally. So you need to either reduce the heat transfer, or enhance the heat transfer in this case, and certain scenarios where you need reduced heat transfer, like if a pipe is carrying steam from the boiler to the turbine, then in that case, the pipe will not be very short. It will be a long pipe through which the steam will be traveling. And if that pipe is exposed to environment, then there is a high chance that a large amount of heat will be lost to environment before the steam actually reaches from boiler to the turbine. In that case, we need to provide insulation. But when it comes to insulation, it has been noticed that simply adding insulation does not help you in reducing heat transfer. So there are a lot of other things that goes into it. So there is a chance that providing insulation can actually increase the heat transfer rather than reducing the heat transfer. It definitely depends on certain scenarios. So one of the scenario is, in order to discuss it, let us consider this particular situation where we have a thermal conductivity K, we have provided an insulation. And let's say the temperature from inside to outside, let's say this is Ti and this is T out. Now we already know the expression, so this is Q is equals to delta T by thermal resistance in total. Okay. All right. So what is the temperature difference? This will be Ti minus T naught, which is, by the way, is fixed, so it's constant. All right. Temperature at the inside of the pipe and outside of the pipe is not changing. That is constant. And when it comes to resistance, we have uh, three resistance technically. One is due to convection here, one due to conduction here, and outside again there is convection here. So let's call this as Hi as the convection, inside, and H0 is the convection outside. So 3 resistances: convection, conduction, and again convection. So let us write them down. The first one will be 2 pi R1 L into Hi. Then the conduction resistance Ln R2 by R1 divided by 2 pi K into L. And again there is convection resistance, so this will be 2 pi R2, which is the outside curve surface area radius, into L into H0. Now since here we are trying to find out at what particular radius or under what condition the heat transfer will increase because of providing insulation. So insulation starts from radius R1 and goes all the way to R2. So thickness of insulation is essentially R2 minus R1. In order to find anything related to maximum value, we use the concept of maxima and minima. That means we usually differentiate this. So differentiate Q dot with respect to R, and then equate it to 0. Okay, so if we do that, initially you will get here dqtr, ti and t naught are constant, so they will just come out. Okay, or we can do this. No, we can do dq dot by dr, and here we will differentiate, so this will be ti minus t naught, and here this is u by v form of differentiation. This will be u into dvds, so u is 1, and then differentiation of this. The differentiation of this, see here everything is constant, so this will be 0. Here 1 upon 2 pi kl will not be there, only differentiation of this will be there. So this is ln r2 by r1, so that's essentially ln r2 minus ln r1, so this will be 1 by, differentiation will be 1 by r2 minus 1 by r1. And then this part will also become 0, differentiation of this part will also become 0, because R2 is constant, L is constant, and H naught is constant. Oh, sorry. R1 is constant, R2 is not constant, because R2 will depend on my guy. This will go only 1 by R2, and here we will have 1 upon 2 pi L into H naught, and 1 by R2. Differentiation will be minus 1 by R2 square. Okay, and divided by this square of this entire thing, so which will eventually become 0, because dq dr it has to be equated to 0. So then what we have is, if we just take this particular term to the other side, we will have 2 pi L h naught 1 by r2 square, and this will also become 0. Sorry, and this part will not actually come. That's fine. So 1 into this. We just have to focus on the resistance, because I mean, like delta t is constant, so there is no point in finding out differentiation of delta t. So here we get 1 upon 2 pi L into h naught r2 square, and this side you will get 1 upon 2 pi k into L by 1 by r2. So here there is a little cancellation of this term, and 2 pi kl, 2 pi, sorry, L, k will not be cancelled. These terms will cancel. R2 will cancel, and R2 will be equals to k by h naught. So if R2 is equal to k by h naught or less than k by h naught, then providing insulation will actually increase the heat transfer. Beyond that particular point, beyond k by h naught value, then providing insulation will essentially reduce the heat transfer. So whenever a situation is given to you, you have to calculate with respect to this particular value, that how much insulation has to be provided on a particular surface, especially cylindrical surface. Next thing that we are going to discuss, sorry, next thing that we are going to discuss is something called as a boundary condition. The boundary conditions are very, very essential whenever you are defining any kind of heat transfer analysis. So a problem is given to you, and if you want to solve it, whether analytically or in a computer, everywhere you have to specify the boundary conditions. And based on the boundary conditions only, calculation will start. Even in case of a computer, if you are doing an analysis, CFD analysis, then definitely you have to provide boundary conditions with respect. Now there are three standard boundary conditions. There are some additional special case boundary conditions. So we are not going to cover special case boundary conditions here. We are going to cover three very common boundary conditions, which will also appear if you are dealing with an ANSYS software. So the first one is a specified temperature. Specified temperature of surface of body. Okay. So let's say we have a wall, and the temperature on this side of the wall is T1, this side of the wall is T2. Here it starts from x equals to 0, goes all the way to x equals to L. Then temperature inside any point on this particular wall can be represented as a function of x and t with respect to distance from the origin and with respect to time also, if it is not a steady state, which is like most of the practical scenario. Then boundary condition on this side of the wall can be represented as t 0 comma t. That means at location x equals to 0 at time t is t1, and this is constant all throughout the analysis. And temperature at location L at time t is t2. So this is one way of giving a boundary condition. Similarly, the second one is specified heat flux. So in this case, suppose we have a wall and this is x equals to 0, this is x equals to L, and let's say some amount of heat is going into this particular surface. This is q naught into minus k into dou, this is dou t at location 0 at time t with respect to dx, whatever value it is. Okay, this is how you can specify heat flux on a particular surface. And the third one is your convection boundary condition. In this case, let's say we have a wall and say convection is happening on this side of the wall. This will be H1 and this is the ambient temperature T infinity minus temperature on this wall is T at location 0 at time T. Okay, this is how you can get a convection condition here. And since convected heat will eventually go into conducted heat into the system, we can also write minus K into dou T dou X at location x equals to 0 time T. This way you can give all the three boundary conditions. So this brings us close to module 1, and next session we will start with module 2, and there we are going to discuss transient heat conduction. What exactly transient heat conduction and how can we uh, do certain analysis with respect to transient heat conduction. Thank you. Let us end the session here.